Does it work? Oh, perfect. So I think that we can get this session started. And I am the policy officer at ESWET. I am Antonella del Figliolo. ESWET is the European suppliers of waste-to-energy technology. Today, I'm very pleased to be here today and to open and moderate this conference, which will focus on how we can decarbonize our future, which is quite an ambitious goal, I can say. And what is the role of the waste-to-energy sector in this goal? Before moving on and before giving the floor to my kind guest, I would like to give you some information about ESWET. ESWET is the association representing the European suppliers of waste-to-energy technology. Our main task is to foster the development and information sharing about waste-to-energy technology and the positive impact that this technology and the sector is bringing to the circular economy and the transition to a more circular economy. Here you can see our list of members, which is also available on our website in case you want to know more about our activities and you want to have some good readings. In today's discussion, we are going to focus on a technology that is gaining always more attention in Europe and globally. And I'm speaking about CCUS, carbon capture, utilization and storage technologies. And in particular, we are going to put the spotlight on the integration of this technology into waste-to-energy plants. Probably we all remember that just before the end of the year, global leaders gathered in Dubai on the occasion of the COP28, and the European Commission President, Ursula von der Leyen, remarked on our important and ambitious goal, climate goal, which are global emission must peak by 2025, fossil fuel must be phased out. We need to find alternative sources, possibly renewable sources of energy. And on top of that, waste remains one of the biggest challenge for our societies because cities are growing and so is the amount of waste that we produce. The European Union is attending to create a more circular system where the focus is on recycling, reuse, and prevention, reuse and recycling. This is the right order. And the waste-to-energy sector is already playing, let's say, its role to meet this goal because it's diverting non-recyclable waste from landfill or reducing methane emissions. And it's providing energy in the form of heat and electricity. But still, we need to integrate new technologies to meet the more ambitious demand of our society and our community. And here comes CCUS. CCUS is finding its place, let's say, in some pieces of legislation, and we will hear about that later during the presentation by our speakers. And it's gaining always more attention in Europe and globally, and we are really recognizing how important its role is for the decarbonization of many industries and many sectors, in particular the waste-to-energy one. So here we can see that there are already some available synergies and some successful CCUS projects when it comes to the integration of this technology into waste-to-energy plant. And it's already a very good signal for our sector, but we really need to accelerate the deployment of this technology and to make it more efficient and more workable for the waste-to-energy sector and for all the other sectors. Currently, all around Europe, there are more or less 70 projects focusing on CC and CCU that are ready to become operational starting by 2030. We will hear about that later. there are two important projects that instead are already delivering on their commitment. And speaking about the Portos and the Northern Lights project, probably you already heard about them. Something very positive, it's the fact that during the last CCUS forum in Denmark, the European Commission announced that 14 project, CO2 transport and storage project, will be in the new list of projects of common interest and mutual interest. So this is a very good signal for the sector and for the industry and for this technology. But some latest projections show that we are not very on track when it comes to the achievement of our climate goals in Europe and globally. That means that we really need to foster the deployment of this technology and accelerate the development of a very strong a very strong European CO2 transport and storage infrastructure. We need an harmonized policy framework that works for industry and that includes faster permitting procedure and less administrative burdens. On top of that, we, of course, need private and public incentives. So we need a very well-done financial mechanism. And we also need to invest in research and innovation program in a way to really develop new and needed technology. So as we embark on this journey, I'm very happy to give the floor to my speakers. We will be with me today. And I'm very pleased to introduce the first speaker of today, Dominic RASSOOL. Dominic is the Senior Client Engagement Lead at the Global CCS Institute, and he will present on the state of play of CCUS implementation in Europe and beyond. Dominic, pardon, the floor is yours.
Thank you, Antonella. I'm just trying to understand how to navigate the slides. Okay. Is it okay if I face sort of, maybe I'll put myself away in the corner here, and then I can see, okay, great, thank you. Okay, well, thank you, Antonella, and to everyone present today. It's a pleasure to be with you. I work for the Global CCS Institute. If you're not too familiar with us, we're a think tank. We're global, it's in the name, and we're spread across North America, Europe, the Far East, and we're actually headquartered in Melbourne in Australia. I happen to be based in London. We're member-based, and we've got a very simple mission, which is to help to accelerate the deployment of CCS globally. So now that we're over with that, maybe it's good to start with places of ambition. On this slide here, you see sort of what was mentioned in the net zero NZE by the IEA in terms of what's needed from various industries by 2030. These are megatons of CO2 on the y-axis from various industries. I noticed that waste is not really on there. And Antonella, you touched upon the need for sort of recycling and waste, and then we end up with some other emissions that are left over. And in the context of all of the other industries, waste is probably the significant opportunity that somehow struggles with scale. And so there's inevitably a high need for CCS there. And the barrier for entry is probably a bit of a challenge for many facilities around the world. Just wanted to make a mention of that. Here is a slide showing you storage around the world, potential storage for CO2 in various geological sites. The point of this is to show you that since very often we hear that, oh, well, is there enough storage in Europe? Is there enough storage around the world for CCS? There's plenty of storage, billions and billions of tons of it. So storage is not an issue. Probably good to get that out of the way as well. Just a list of CCS facilities. This is a bit outdated, probably by about a year or two. But it's the theme that I think is interesting for us to see here, or rather the trend. which is that, I don't know if you can read these slides, these images here, but you'll see that low-cost capture, enhanced oil recovery, and generally some sort of low-cost transport and storage have been the main kind of, if you want to call it, enablers for CCS projects that have gone into operation. And they rely on a revenue from EOR, enhanced oil recovery, and in terms of financing, they've all been sort of invested in from large organizations that can afford to pay for them off their books. So you can hopefully see where I'm going, which is to try to get to the opposite of this. But this proves that if there's a business case and the risks are sufficiently understood, probably difficult to infer from this, CCS does happen and can be deployed. But there are barriers to deployment. We did a study a few years back. I don't want to bore you with these details, but on the far right of this image, you see that there are hard to reduce risks. So once you've addressed and managed all of the other sort of technical risks, you end up with three sort of groups of risks, if you will, that are very, very difficult to pass on to the private sector for them to deal with by themselves. That's the policy and revenue risk, the cross-chain or interdependency risk, and the storage liability risk, especially long-term storage liability. We're talking tens, potentially hundreds of years of storage, right? So we believe that government is best placed to address or manage these risks. So from a policy perspective for revenue, it's important that government assigns a sufficient value on the CO2 that is to be captured, transported, and stored. So then there's a business case for it. The cross-chain risk, which is to do with the interdependency, both from the sort of project development phase through operation between the capture facility, transport, and storage sites, being that if one of them goes offline, then, for example, there's nowhere for the CO2 to go or to come from. So that needs to be addressed. And typically here, I've just mentioned hubs and clusters. I'll see if there's time to touch upon this later. Long-term storage liability is basically you can't leave a company to be liable for all of that CO2 over an indefinite period of time. At some point, that liability needs to be addressed, ideally transferred to probably the state that is best placed to sort of absorb that risks, because governments are not in the business of making profit. They're in the business of delivering a public good. And I think addressing climate is probably one of these public goods. So this is to say that all of these can really be addressed through policy and through some kind of, let's say, PPP partnership when you come to networks, something to enable networks. So I'd mentioned that deployment has relied on this sufficient value being placed on CO2. And typically that has been when there's an offtake agreement between the offtaker, which would be a transport or storage provider, and in that process there's been clear sort of framework for what happens to the liability. We've seen this happening in the US since 1974, I think, the Terrell gas plant being the first one. So it's happened before in a sort of a haphazard way, mostly on a purely commercial level without clear incentives from government. And I'm not going to read off these. I think you've probably done that yourself. But ultimately, it's repeating the same points that I'd made earlier. But for us to really achieve deployment of CCS so that it meets its full potential, including in the waste-to-energy sector, we need to find out how to scale this. And scaling comes with obviously policy and that government intervention. And I think without going to the detail of placing the value on CO2, governments will decide what they want to do with that. That can be a tax credit, that can be the EU ETS, whatever it is. In the US, they've got the 45Q. You may have heard of this if you've been sort of reading a bit on CCS. But really the challenge is also financing. Not many, for example, in the waste industry, not many organizations are able to fund CCS projects off their books. So they need project finance. And project finance is to play this huge role in sort of allowing deployment across these smaller emitters that otherwise would not be able to access financing. So once you've got the business model in place, that financing becomes important. And this is just a theory of project finance, so I'm not going to spend too much time on this. But ultimately, you know, the risk isn't on the individual company. So long as you can prove that there are sufficient cash flows in the future, you're okay. That said, there are risks in CCS, in developing a project and operating it, that banks are unfamiliar with. So they'll probably charge a premium, not just the lenders, but also the insurers for CCS projects. And inevitably, you end up with only so much money that you can raise. So you end up with a funding gap. And again, it's the role of governments, such as through multilaterals, et cetera, to come in and to close that gap, knowing that they can take on certain high sort of risks, or risks that are not well understood and inflated or overinflated by the private sector. And over time, as they get to better understand these risks, then they can start to pull out from, let's say, concessional financing for project finance. Here you just see some examples of the different actors that there are in this space. Nothing new. It's been done before elsewhere, so there shouldn't be really any surprises. Why would the banks want to do it in the first place? Well, it's pretty obvious that they've also committed, everyone's on the net zero bandwagon now, and they've committed to reducing their emissions. And that doesn't include just their own operational emissions, but also their portfolio emissions. So they have the decision of whether to engage with their clients and help to fund CCS and find ways and means to offer that financial support or product or package, and also work with governments to find out where government can come in with that concessional financing. But ultimately, they need to deal with their portfolio emissions. And they could also choose to sort of kick the can down the road and leave that problem to another bank to solve that maybe hasn't made such commitments. But that is not sustainable. We don't reach net zero. I'm sort of moving away from that topic of financing now, but I just wanted to broaden out into, you know, the importance of CCS across various industries. I've managed to get some waste to energy revenues on the third sort of graphic you see there on the right. And this is the revenues as a percentage of GDP compared to, let's say, the NDC commitment of these countries. We'd actually done an interesting study on various industries and all the different countries, but really it's to show the sort of level of buy-in that countries must have for CCS in those spaces. This is just indicative, but it's quite interesting, nevertheless, to see that globally, a lot of the players are from Europe. So relative to others, Europe probably should be a bit more interested in CCS for waste. But anyway, there's some good news. Things are changing, yep. The EU's got a CCS target in terms of storage. So to reach that, obviously, it's going to need CCS. And I think there was a leak recently where we saw some interesting developments in the news. So the Industry Act is probably going to be the enabler for this. And that will translate into various other policies that are very interesting. So it's looking promising. Antonella mentioned Aalborg in Denmark. Recently, we have seen also other developments in Europe, Porthos as well, being approved and going ahead. So these are really promising signs. And I think what's interesting, if we also include the UK in that conversation, is it's the first time in the world that we're seeing this kind of programmatic approach to CCS, where while it's slow moving initially, it can pick up pace and there are good precedents being set. So that's very good. So the US is, I mean, the UK is kind of the same. They've got some elegant business models for each of the different sectors there. The US has a more sort of blanket approach, very simple, 45Q. And that's all been enabled through the Inflation Reduction Act. Kingdom of Saudi Arabia has also announced a target. And in Brazil, we're seeing some developments there as well. This is all to say that ultimately, if governments really want to and they make the commitment, it can happen. And what I've told you so far this morning is it has happened. So scale is just the question now. Talking of which, here's the chart showing you the sort of project pipeline around the world. This is from our latest global status report. I don't know if there's a little laser on this, but if you look at the final bar, 2023, it does look like exponential growth if we're starting to look from 2018 to 2023, let's say. But I am more interested in looking away from the hype a bit, which is the sort of very light green and indigo/teal bar. And you look at the bottom two bars, which are the ones in operation and the projects in construction. We're seeing that massive jump of projects in construction from 2022 to 2023. So the good news is that things are beginning to translate from announcements, very early development, to advanced development, and then getting sort of over that barrier of making it into construction. So there's meaning, in fact, to the sort of the lighter colored bars. And that's good news. It's the biggest jump we've ever seen in CCS moving into construction in terms of the project pipeline. Where that's happened around the world, well, you can see that those in early development are mostly sort of Europe, North America, and the Far East. There's a lot of activity going on in the Far East as well. And there are sort of, well, we get to speak with some of the countries that are in Southeast Asia as well, and we see a lot of development in terms of commitment there and interest in how to implement the right policy and legal framework, etc. So that's not represented here on this chart, unfortunately. Then in advanced development, operation, etc., we see that the US is still very dominant in that space. So once Europe turns some of these green balls into sort of blue ones, I think we'll be in a much better place. And there's no reason why, you know, a good percentage of these don't translate in that direction. So probably one for the last mention here while we're on the topic of project pipeline is transport and storage. I'd mentioned in the past that enhanced oil recovery used to be the dominant sort of player for how CO2 is stored. That's changed quite wildly now, and we're seeing that it's dedicated geological storage that's the only game in town almost these days. So most of these projects coming online are not doing anything with extracting oil. They're literally just storing CO2 in geological subsurface because the business model allows them to, right? So that's to re-emphasize that point of get the business model right, make it based on climate policy, and as long as the cost of capture is below whatever the incentive is, then we're good to go. On the left, you see all the various modes of transportation. Pipeline is still the dominant one, but we're starting to see increasing interest in things like rail, for example, or shipping as well, especially in Europe. So that's quite interesting. So this is just to touch upon networks. We talked about the cross-chain risk and interdependency risk. So these figures are just identifiers. They're not literal sort of absolute sort of values of the number of networks. They're much lower than that. Each dot, you can say, is a network. So you can see how that is spreading around the world as well as the sort of main modality for implementation and deployment of CCS. Because networks just reduce the cross-chain risk. Networks give you benefits of economies of scale. They allow clusters to develop. And when we're thinking about waste, and we think about scale in waste, one of the barriers to implementing CCS and waste to energy plants is the scale. Networks allow you to somehow, to some extent, overcome that because you're sort of partnering up with some other entities. You're sharing the cost of transport and storage. Right. So in summary, we've got the Net Zero Industry Act from the EU. We've got the CCUS strategy that's in place. I've even seen a couple of pieces of literature where there is talk about CCS and waste to energy and the need for it once all of the recycling targets are sort of met, outlined. And we see Netherlands, Denmark, and the UK progressing their policies and projects. Incidentally, in the UK last week, DRAX was approved. That made the news, and that's really exciting stuff because it's the first BECCS project in the world of that size, certainly. So very promising signs. Just a bit more summary around Europe. We've got the EU ETS. Price has stabilized quite high despite all of the various potential headwinds that we faced globally and in the region. And we expect those prices to continue rising. And that means that more and more industries become interested in CCS because it becomes viable for them. Grant and capital support, EU Innovation Fund. Then we've got these national incentives like the SDE++ in the Netherlands. Northern Lights in Norway enable us to capture CO2 in some parts of Europe and transport it up there. Porthos I've touched on already, and there are others in development. And the storage directive, albeit a little bit sort of light, that sort of helps to set a foundation for various EU nations to build upon. And we as an organization like to step in and to help them to sort of at least develop that framework a little bit further. So I think Antonella covered this, so I'm not going to waste our time covering the projects in Europe. You kind of roughly know what they are. If you want more information, on our website. And here's some stuff to look out for. And lessons learned, I'm just going to whistle through this, I'm afraid, because I'm getting the indication that I've run out of time. So thank you very much.
Thanks a lot. Thank you. I can give you back your place. So thanks. I was telling you that I can give you back your place and then can take back mine. So thanks a lot for all these interesting input that you shared with us. I think it was a an extremely interesting presentation. And if I may, I mean, just a question came to my mind while you were speaking, and I would like to know, I mean, you talked to us about where we are, what we need for the future, and I would like to know how the European community is reacting to the deployment of CCS broadly. So also in terms of public opinion, how do you see it?
Yeah, thanks, Antonella. That's a touchy subject. But I mean, the private sector is obviously very cognizant of the need for CCS, right? They're stuck between a rock and a hard place. Some of them don't have many other options, and the ones that they do that are not CCS are more costly. Some governments are sort of not doing the bare minimum, but let's say they could be more helpful in allowing things like onshore storage through well-characterized sites, etc. But to your point about the European community, there's a problem with societal acceptance of this group of technologies, especially as regards geological storage. I don't think that people fully understand how that works, and for worse, they end up coming to their own conclusions about what CO2 storage means, and eventually there might be an explosion, et cetera, et cetera. So we and other organizations like yourselves have work to do to improve that level of acceptance, improve the level of awareness on the technology, and that then will make it easier for decision makers and politicians to sort of make that part of their manifesto, that they will commit to CCS. In some parts of Europe, especially it's funny because there's a split between North and South, and in Northern sort of Europe, the Netherlands, Denmark, etc., Belgium, that acceptance is fine. And the Danes have, done a fantastic job of engaging with their people on that level of acceptance. And once they've seen the economic value of CCS, and once they've understood that storage can be very safe, it can be extremely long-term, and in fact, you're just putting the CO2 back whence it came, then everything moves forward more smoothly. And I think that's part of the reason why we've seen Denmark advancing very, very quickly in the last 2 or 3 years.
Thank you. That's a very interesting reflection that we will work on, and I think we really need to address this problem in the future. It's one of the biggest problems that we have when we speak about CCUS. Now, would you like to move on, and I'm very pleased to give the floor to Alain Bill. Alain Bill is not only the member of the ESWET Technical Committee and CCUS Working Group, so thanks for your participation, but he's also the Vice President Global Sales Business Development, High Pollution Control Division at ANDRITZ. And Alain is going to present the ANDRITZ concept for CCUS ready for waste-to-energy plants. So, Alain, the floor is yours. Yeah.
Good. Thank you, Antonella, for the introduction, and also for Dominic for the earlier setting the scene, so to say, when it comes to the quantities and where to go with the CO2. So let's, I just need maybe your help here to get the green one. Yeah, that's, voilà. Good. So the presentation we have prepared here with the ANDRITZ team is related to, concepts to be applied for the capture of CO2 at a waste-to-energy plant. There are actually many concepts which can be used. I will not discuss all of them here. We can discuss them separately if needed. But you see it here on the graph is that currently there are many types of flue gas treatments which are available on the existing waste-to-energy plants. And there are a few requirements from the technology when it comes to cleanness of the gas prior to your CO2 capture or CO2 separation unit. What you see here is on the far right, the plants which will be equipped or have to be equipped with CO2 capture will require a fair amount of pre-scrubbing, pre-cleaning, so that in combination with the selected technology, you will be able to have the lowest possible emissions to, so to say, have the most efficient CO2 capture. So it's going to be, let's say, an analysis to be done, which is to some extent a case-to-case analysis. We cannot, have one solution fit them all. And for that, basically, there are a few questions which you should ask yourself. For example, is your interest to capture CO2 on existing lines or on the new lines which you are planning? Which is your CO2 strategy? Do you wish to capture the entire quantity, or just, for example, the biogenic share to be able then to value it as e-fuel? And then, very important, and I think this is where there are still some questions, and we hope legislation will now progress quickly in Europe, is where to go with the CO2. For sure, the capture of CO2 of a few tons maybe per day are possible, because you can still, treat the CO2, transform it. Eventually, you have a kind of storage area which has a limited permit for that amount, but when we start speaking about 100 or 1,000 tons a day, then you really have a logistic element to consider for the CO2 transportation and storage, and that really needs to be addressed. Then when it comes to the CO2 capture technology itself, or the CO2 capture unit, today there are many options. So we need to understand if you wish to have a kind of a scrubber or a membrane or a solid absorption or another option, and that technology will impose some requirements on the level of contaminants which are allowed into the flue gas, so to say, especially if you go into some solvent-based capture system. There are levels of acid gas and NO2, for example, which have to be controlled so that you can preserve, so to say, the integrity of the solvent. Then, and I think my colleague from lab will discuss that more in detail. I will not touch upon it, David. On the capturing CO2 requires energy depending on the technology you select in different forms, so that needs to be well thought in the integration of the CO2 unit into the plant, and then of course what is the level of purity you wish to have in the CO2, depending on the use you might have. And there are today a few specifications which have been published on quality of CO2. For example, for the Northern Line, you can find them on the internet. They are pretty strict, when it comes to levels of oxygen, for example. Maybe they will relax it a bit, but this is also important element for technology providers as us to figure out which quality do you want the CO2 to be. And then, of course, it's at the end a point of the return of investment that needs to work. And then, of course, if you have the possibility to store it, the point of using the CO2, converting it into a valuable fuel, I think it's a big opportunity here for the waste-to-energy operators, especially in terms of taking the biogenic share of the CO2. I think that's it for this slide. Then here are two options, for example, two concepts which could be applied for the waste-to-energy sector. The first one is the well-known absorption, desorption concepts, which can where you can have different solvents. Amine-based solvent is the most common one, but there are also HPC solvents which can be used. All the system will start, with a pre-scrubber to make sure that you fulfill the requirements of the capture installation. Removal efficiencies can be obtained typically up to 95%. The quality of the CO2 or the purity of the CO2 can also be set. You just need to add on the desorption column a few elements of additional, dewatering, then filtration with active carbon, eventually calcium permanganate filters, just to get to the level of purity you need. When it comes to energy consumption, there is here a big element. It takes a few gigajoules per ton of CO2 to capture the CO2. Of course, the integration into the heat cycle of the plant is going to be a winning concept. There are, of course, discussion, especially when you work with some solvents, about secondary emissions from the absorption column. But what we have seen, and I think it's also demonstrated in the Netherlands, if I'm not mistaken, if you do properly the design, of the absorption wash with some water wash and some acid wash, you can really minimize the the release of some degradation components into the atmosphere. So I think here, if the design of the installation is well done, it should work properly. Now, when we come to the larger installation, most of the installations today are in stainless steels. As I said, or as we said, they are to some extent small, nevertheless already sizable amounts, a few tons per day. Should we go to very large installation, we would certainly recommend to use a different material, which is concrete with some lining, that will make the cost of the scrubber much more attractive. So that's for the first technology. On the second one, and this is maybe for customers who are not aiming at capturing 95%, there is an option to apply separation based on membrane. And in this case, you would have, you wouldn't need, let's say, the energy from the steam to regenerate the desorber as in the first case. But here you would then, of course, substitute that with electricity to be able, to run all the fans and the various pumps or vacuum pumps to drive the process through the membrane. So it has some advantage. It's very compact. It has maybe one module removal rate around 60%. So you would have then, of course, to stack them if you want to have higher levels. But maybe if you are only interested of 50% of CO2 removal, your biogenic share, so to say, that could be an option. The technology is not, at least in our company, is not yet available at the same level of maturity as for the amine scrubber. We would test it and have some mobile applications for it. But at this present time, we are not able to give guarantees. Voila, I think that's what I wanted to say about these options. Now let me come to maybe this slide. If today you are considering to build a new line and to have it CCS ready, this would be typically the flue gas line that we would recommend prior to the CO2 capture unit, because such a line, a flue gas line, will enable you to make sure that you can then directly install the CO2 capture unit and separate the CO2. So typically here, we would have a first flue gas treatment, which is based on a semi-dry sorption with lime, hydrated lime, where we would do a first, elimination, abatement of the acid gas, as well as with the active carbon. We would take, of course, the heavy metals, the dioxins and the furans. Then we would go into the SCR to remove the NOx. And as I said, most of the process for the CO2 capture are very sensitive to the concentration of NO2. NO is not so much an issue, but NO2 can be tricky. Then we would go into a second stage of pre-scrubber and caustic scrubber before recuperating, the energy in the flue gas condenser. What we also try to do, is to make a good use of, let's say, the water. So the water from the pre-scrubber can be re-injected into the furnace. That's not an issue. And the liquid stream from the caustic scrubber, the second caustic scrubber, to further reduce, the acid gas, the SO2, that can be evaporated into the semi-dry sorption. So we would, of course, minimize the effluence, the liquid effluence. There is, of course, a bit of effluent from the flue gas condenser, but that can be treated and disposed then into the wastewater stream. But by having such a scheme, which looks, of course, complicated, we can go to these ultra-low emissions, which will be required by the CCUS capture units. Of course, David will mention it a bit more, but there is an interest, of course, of taking good use of the energy recuperated in the flue gas condensing unit in case it's not used for district heating, which could be, of course, a challenge in the operations of waste-to-energy plants when they are connected to a wastewater treatment plant. Voilà, I think I'm coming to the end of the short presentation. We'll take questions, of course, I think at the end. But today, especially when looking at the technology based on absorption, desorption concept, there are possibilities to implement it at plants, and should, let's say, your company not be ready with one or the other concept, most of the technology providers offers today some mobile applications where you can test one or the other solvent or one or the other technology before going, let's say, to the very large plants removing a few 200 tons, 100,000 tons a year, or even going to higher quantities. I think that was the last slide I had, and I thank you for your attention.
Thank you. It works. Good. So I have quite an immediate questions for you, and then we can pick more questions after all the presentations. And I would like to know if you can give us an order of magnitude of the percentage of it used to regenerate a mine, or more generally to capture the carbon.
Yes, so that's certainly an important element to size the installation, and also to see at well, to determine the cost of operation. What we have seen, depending on the type of solvent which is used, we see values between I had in my slide 2.7, 2.5, up to 3. I have seen even 3.3 gigajoule per ton of CO2 capture. So I'm maybe not expressing that in percentage, but in numbers. Now, this energy is the energy needed for the desorption, so to say. Of course, absorption mechanism is exothermic, so we recuperate some of this heat, we integrate it into the entire system. We have been working with our first pilot on another segment, on the cement segment, where there is not so much steam available on site. Unlike the waste to energy or maybe other segments. So that has pushed us to consider the heat pumps to reduce to some extent, or to substitute, let's say, the thermal heat with the electricity of the advantage of the heat pumps. So there we could basically find when well done, potentials of reducing this energy consumption into the absorption and regeneration unit. So I think there is a excellent opportunity, despite the fact that the heat pumps are very costly, but over the lifetime of the plant, 20 years, even if the capex is higher, the savings you will have in terms of electrical consumption is going to be to the benefit of the use of heat pumps. So that's the recommendation we will do.
Thank you very much, Alain. It was a very interesting presentation as well, and I think we got some very and extremely useful information. Thanks a lot. So now I think we can switch again, and I'm happy to introduce to you David Boyer. David Boyer is member of ESWET Technical Committee and is also Sales Director at Lab, and is going to present us how to maximizing heat recovery in waste-to-energy plants and synergies with carbon capture for decarbonization. Thanks a lot.
Thank you very much. Good morning, everybody. So I'm going to present how to increase the heat recovery within a waste-to-energy plant by implementation of flue gas condensation in the flue gas treatment, and also how to connect this additional heat recovery to the future or later installation of the carbon capture plant. So a quick presentation of Lab. Lab, we are a French process and engineering company. We were belonging to CNIM during more than 20 years. But since 2021, our 100% ownership is the company Martin GmbH from Munich, that you may know as a supplier of a great system for a waste-to-energy plant. So we are roughly 150 people. Headquarters is in Lyon, and we have one main office in Stuttgart in Germany, taking care of the German-speaking market. Yes. So our main activity is flue gas treatment for several applications. So the main one is waste to energy, as I said before, but we are also working on the biomass to energy plant, as well as the sludge incineration. And we have developed in the last years this flue gas condensation system for transfer of heat to the district heating and to increase the plant efficiencies. We have also an activity for the marine activity, where we deliver a system for desulfurization as well as a catalytic system for NOx removal. So flue gas condensation, what is it? First, you need a flue gas treatment for the dust removal, acid gases neutralization, heavy metals and dioxin and furans removal. And then two technologies are available on the market. It could be by what we call a polishing scrubber, a plastic scrubber which equipped with a packing, with an external water-water heat exchanger, which transfer the heat to the district heating network on the left side. Or it could be what we call a direct heat exchanger, means that you have a direct contact of the flue gas and the district heating network, and two technologies are available on the market. It could be a tubes heat exchanger or a plate heat exchanger. So now I'm going to show you some free example of a project that we have developed and built in the last years of this flue gas condensation. So the first one is starting from north of Europe in Kaunas in Lithuania. For Fortum is operating the plant, and it was a greenfield project. And we installed first a semi-dry system with hydrated lime injection and combined with a condensing scrubber in two steps. First step with connection, transfer of the heat to the district heating, and the second step, which is humidification of the combustion air, means we put additional water on the combustion air, which is used for the combustion, in order to increase the heat that we will recover on the flue gas treatment side. So you have some technical figures on the slide. I don't think I need to repeat. Some photos of the plant. It's always nice to see photo and the sun shining in Lithuania. And as you can see, it's a complete outdoor installation, flue gas treatment installation. And on the right side, you have the size of the condenser. I think it's 30 to 35 meters height. Second example is Brescia in Italy, in north of Italy. So Brescia, the city of Brescia has a long history of district heating network within the city. And this project was a brownfield project, means that the plant is existing for, I think, 20 years. And the flue gas treatment was a dry system with a maturation silo. And A2A decided, in order to first to lower the emission and to fulfill the new BREF Batael requirements, to install downstream of the existing dry system condensation unit with a polishing scrubber technology as well, connected to compressor heat pump, and also downstream a SCR system on their 3 existing line of 42 tons per hour. So it's quite a big plant. So also some nice photo of the plant. Maybe you have seen it already. It's along the highway in the city of Brescia. You have on the right side the new installation, and the bottom picture represents the compressor heat pump. Last example is city of Hamburg, Borsigstraße in Germany. Also an existing plant where we have installed 3 condensation units, 2 on the existing waste-to-energy line and 1 on a biomass line. And here the technology was different. It's a plate heat exchanger, as I presented before. And which is interesting is it's in 2 steps. The first step is a direct connection on the top of the sketch. Is a direct connection of the heat to the district heating. And the second one is a connection to an absorption heat pump that we deliver as well. In order to really optimize. I broke it, no? Hello? Yes. And the second stage connected to absorption heat pump to really increase the heat recovery within the flue gas treatment. Some photo here, it's absorption heat pump. You can see the difference with the compressor shown before and the plate heat exchanger on the bottom. So this is really interesting, and it is also preparing this flue gas condensation step for the future and the carbon capture unit. In lab, we are promoting for the carbon capture system conventional as presented by Alain as well, the amine solution with absorption, desorption. And we are working in the way that our main role in lab is flue gas treatment. So we have typical flue gas treatment, then we retrofit, we update to the low breath, which is the regulation now, not the low breath, but the breath, which is the regulation. And then we have partners for the carbon capture unit itself, means for the absorption, desorption, we work with partners in Netherlands called Broesche Process Technology. And for the compression liquefaction unit, we have also partners which are much more specialized than us for this part. Our approach within lab is to offer solution within the wastewater plant. We are not interested by transporting the carbon capture from the plant to the port or to somewhere, because this is not our job. We really focus on the waste-to-energy plant itself and on the flue gas treatment. So what we are offering to our customer is, at the time being, feasibility study with the design of the carbon capture unit, how it is integrated on the existing plant. Because the main issue for the carbon capture unit is, as you know, is the heat which is requested to operate such a plant. And for that, we have really an adding value with our know-how on the flue gas treatment. And then we provide information at the end, which is the most important for our customer, about CapEx and OpEx evaluation. Then we provide information. I think everybody is doing the same, but regarding the design, the PFD, PID, 3D modeling, arrangement, and so on. So at the conclusion, we think that flue gas condensation is a must for increasing heat recovery within a waste-to-energy plant, and to achieve high performances on the emission, as I said before, the breath emission limit. it prepares for the carbon capture unit because the flue gas condensation is conditioning the flue gas to the right temperature of the carbon capture unit and also to improve the low deterioration of the amine that will be used. Carbon capture is feasible in a waste-to-energy plant. I think it will be the conclusion of today. And everybody agree on it. And it's already ongoing. Yeah, you showed the example on the plant in Netherlands, existing plant, but there are several projects under development. And the most important, the most critical is really the heat integration, and it's where we see source of optimization and where we expect also to be present and to support our customer. I was too quick? Quicker than the previous one, but...
No, absolutely.
Okay.
It was perfect. Thanks.
Okay.
Thank you, first of all. And in one of your slides, you mentioned that one of the main service that you provide to your client is information about CapEx and OpEx, an estimation of cost. Can you give us some more information maybe about that?
Difficult question for sure, but it's really depending on the available heat in the existing plant. Alain mentioned you may need to add heat pump to find some alternative for the heat. I would say that till now, what we have done regarding the feasibility study, rough figures would be between 120, 150 euro per ton of CO2. Means regarding the capex for the new plant and the opex for 15, 20 years. Is the rough figure, but this is where we are at the moment. It should decrease in the future regarding the capex, maybe, but this is a rough estimation that we can say today.
Okay, thank you very much.
But I will not sign.
Okay, we will keep for ourselves then. Thanks a lot. Now I think you can exchange your place with Fabio Poretti. Fabio Poretti is Technical and Scientific Officer at CEWEP. CEWEP is the Confederation of European Waste-to-Energy plants. And he's speaking today about bioenergy with CCS and CCU for waste-to-energy plants. What are the challenges and opportunities? And Fabio, the floor is yours.
Bonjour. Good morning, everyone. Can you hear me? All clear? So first of all, let me thank Antonella. Grazie. And thank you, ESWET, for the invitation today. I'll try to give you a more broader overview at EU level of what's happening in Brussels and also how the European waste-to-energy sector is looking these topics and what's its vision on a climate perspective. So, first of all, I work at CEWEP, and CEWEP is the Confederation of European Waste-to-Energy Plants, and differently from ESWET, we directly represent the operators and owners of waste-to-energy plants all across Europe. And in this slide, you can see our evergreen map with the distributions of the plant in Europe. So two key numbers for you. We have 500 waste-to-energy plants treating about 100 million tons of residual non-recyclable waste every year. So just one slide to remember what we do and why we are here today. So even before talking about carbon capture, let's remember that we need waste-to-energy as a service to society to treat safely all that residual waste that is not good enough for recycling. And this is the essential task given by waste incineration facilities today. But by doing so, as you can see, actually both circular economy and climate mitigation, they go hand in hand with waste-to-energy, because by thermally treating waste, we also produce important quantities of electricity and heat that can come back to our cities to power them up. And just by doing so, we are already saving some CO2 emissions because we are substituting some fossil fuels. And so we are reducing dependency on fossil fuels and we are saving an equivalent amount of CO2 emissions. But in the future, I like to see not just waste to energy, maybe we can call it waste to value, because not only energy can be recovered from our facilities, but also materials. So for example, the bottom ash, the residues of the combustion process, they can be sent to recycling activities, and this also saves some CO2 emission savings, raw materials. And in the future, more and more, and that's why we are here today, also the other outlet that can be recovered is CO2 as a feedstock, for example, to the chemical industry. So another good example of circular economy. So why carbon capture? Carbon capture is and can be indeed an extra piece that has the potential to really achieve a net negative balance. And this was also acknowledged by the IPCC in 2022, and we were very glad to see this. As it was mentioned already twice today, in the picture you can see the waste-to-energy plant of AVR in Duiven in the Netherlands. So I don't have a laser, I think, here. But anyway, in the back, you can see the waste-to-energy plant itself. It's a conventional waste-to-energy facility, 2 lines, great furnace. And at the front, that's where you can see the existing carbon capture units. Here at AVR, they've been doing this for already quite some years, and they have been collecting good knowledge and experience in capturing CO2. So the carbon capture unit is not a full-scale one. It has the capacity of 100,000 tons of CO2 per year. You can see on the very right the scrubber, and then the absorber, the chiller, the scrubber, absorber, the desorber, and the stripper, and then the 4 storage tanks where CO2 is stored, and then trucks come, take the CO2 and send it to greenhouses. So in the Netherlands, they have a very good business model for the use of CO2 in greenhouses for the cultivation of vegetable, flowers, and so on. With this slide, I just wanted to include one slide on our current flagship project. Our climate roadmap is an in-house project that we developed and we launched in 2022 with the goal to make some clarity on what is a climate balance of a waste-to-energy plant. So very quickly, if you see on the left, that's pretty much what is already happening today. So at the top, you can see what are the direct emissions of the waste-to-energy plants. Because inevitably, by thermally treating the waste, yes, we have some CO2 emissions out of our stack. But the first thing is that about 60% of these emissions are biogenic, the green part. And then I leave it to Jürgen later to explain better how to account for biogenic versus fossil. Okay, but pretty much as EU averaged, of course it depends on the waste composition, 60% of the CO2 is biogenic, and the remaining 40% is fossil. That's the gray bar. And that gray bar, it's pretty much inevitable emissions that you have, because those are due to the process. So those are linked to the nature of the plant itself, which is again treating safely the waste that we produce as consumers. And those are due to all those mainly non-recyclable plastics that arrive to a waste-to-energy plants, and we have to treat them. So yes, we have some positive emissions, but if we also adopt a life cycle thinking and we also consider what are the avoided emissions, so for example, what I mentioned before, the avoided CO2 for the equivalent production of electricity and heat from fossil fuels, and some savings of CO2 from the recycling of bottom ash, and I throw a line, I can see that the balance on an LCA perspective is already zero today, okay? And this is the first good news, that on a life cycle perspective, a waste-to-energy plant today can be already considered climate neutral. But of course, it's, let's say, not enough because we have some very ambitious climate targets at EU level. So we have to think of what the sector can do more. And in the future, this can be achieved with carbon capture if we add another piece on top that really has the potential to create a net negative balance, and this is already a conservative assumption. So I'm going to stop here. I'm not going to enter into the numbers, but if you want, I was the leading author of this work. I also have some copies with me today, and you can find it online, so feel free to ask anything at the end. So another slide and a disclaimer, just for clarity. We have to make, in terms of climate dictionary, we have to say something, because what I just shown, the climate roadmap adopts a life cycle thinking, okay? But there is a difference between talking about a climate saving or a climate reduction differently from carbon removal, okay? Because a carbon removal is intended only when biogenic CO2 is captured and is either permanently stored into the ground as CCS or is chemically bound into a long-lasting product permanently, okay, with a CCU application as a mineralization opportunity. And where is the potential of the waste-to-energy sector? That, as I said, about 60% of our emissions are biogenic. So if we capture them, we indeed have the potential to generate carbon removals. And I've been around yesterday here in Nantes, and I heard a lot of interesting discussions about carbon removals and why they are needed. So maybe no need to say why we will need them. But carbon removals are getting more and more interest because we have more and more company and big companies like Google, like Microsoft, that are interested in buying removals to offset their emissions or their historical emissions. But not only companies are interested in removals, but also the European Union itself will need carbon removals if we really want to achieve climate neutrality by 2050, because in 2050 we will still have some inevitable emissions that we will have to counterbalance with some negative emissions. And that's where also the sector can play an important role and has a big opportunity. And that's why, as CEWEP, we are now working on developing the methodologies for the certification of carbon removals from BECCS, and especially from waste to energy. We are part of the expert group of the European Commission on carbon removals that will develop the delegated acts to then set again the certification methodologies for BECCS and for waste to energy. So carbon removals, it's an interesting opportunity to stimulate investment in CCUS, but the question I always get is, Fabio, what is better, CCS or CCU? And we can spend the whole day deciding and talking what we want. It's more, I think, of a philosophical question. In our vision as CEWEP, we think we will need both, and in this sense, we are totally aligned with the vision also of the institutions. And actually, waste-to-energy plants operators in Europe are looking at both possibilities. It really depends on the local conditions and the business case that you can develop. So I will give you very briefly two examples, one on CCS, and this is probably one of the main renowned one. This is the project in Oslo, in Norway, where they intend to build the first full-scale CCS system that, once in operation, will capture 400,000 tons of CO2 per year. And this is part of the broader Northern Lights project. As you can see, if I want to build a full-scale facility, these toys are not little, okay? They require a big space. The footprint is massive, so the full-scale carbon capture unit is as big as the waste-to-energy plant itself. And then, of course, there is still a big matter of costs, and Oslo had to face a cost increase, and they had to stop for a moment for doing a reevaluation, a cost phase reevaluation. But the company, as a city, is really committed to pursue and continue and finalize the project. Let's move then to the Netherlands. So we move to the waste-to-energy plants of Twence in Engelo, where you can see the development with the rendering of the absorber and the stripper on the right, and then on the left, the CO2 liquefaction units. And I can tell you that's the other good news, that the plant, it's pretty much done. This is a picture that was sent to me by my Dutch colleagues last year. And so the plant is finalized, and it's meant to start operation at the beginning of this year. In Duiven, in Engelo at Twence, at the beginning, they will also use, they will also capture and then use CO2 in greenhouses, because, as I said, in the Netherlands, they have a very good business case for the use of CO2 in greenhouses, which is also subsidized by the government. In fact, this project received support by the Dutch government with the SDE++ mechanism that was also mentioned by Dominic. So here's some figures on the CapEx and the OpEx. And then it was mentioned already before, let's remember that these toys are not for free only economically, but also thermodynamically, because the energy penalty can be quite severe. But in relation to the two previous presentations, I do also believe that flue gas condensation is somehow necessary if also you want to implement carbon capture, and that's also what we consider and we assume in our roadmap. Moving on quickly, I could go along with other projects. I would stop here with this slide, and I don't want you to read all that is written. It's just to say that carbon capture projects are developing not only in Norway and the Netherlands, but operators in Europe are looking at carbon capture, and many more feasibility studies are going on frequently. So if you're interested to know more about this, you can find online for free this paper that condenses all the findings of our climate roadmap with an overview, with that list of existing CCUS initiative applied to the waste-to-energy sector in Europe. And at the moment, we can count about 60 active projects and initiatives being developed. So the momentum is growing. The sector is really looking into CCUS, but we cannot do this alone. And we still have to face several obstacles. So very quickly, to go towards the conclusions, what are the barriers that we still have to face? First of all, as I said, CapEx and OpEx is still an issue. And then we are lacking of revenues models, so how to finance these projects, maybe by extending the innovation fund or thinking of mechanisms like carbon contract for difference. And then the famous chicken and egg problem. Should I build first the carbon capture unit, or should I wait that the CO2 pipeline is going to pass by? And this is difficult, and that's why we need to match also emitters with, for example, storage opportunities and hubs. And then public perception was also mentioned, so a lot of fears about, for example, storing CO2 into the ground. And then what we need is really the development of all the policy and regulatory framework. So on this, and this is my last slide, what is Europe and what is Brussels at the moment doing for the uptake of CCUS in Europe? What I call the Trinity was already mentioned. So first of all, the certification for carbon removals. The legislative process is about to finish. It should be set in the middle of 2024. In the meantime, the expert group will develop the methodologies to establish removals, for example, from BECCS. And in the future, we will know that in 2026, if removals will be matched or not with the EU ETS. The second tool is the ENVEA. It was also mentioned by Dominic. So this was in reaction to an American action. So Europe came out with the ENVEA to make sure that net zero technologies are produced in Europe. They made a list of strategic net zero technologies, including CCS, with a goal for member state to have an injection capacity of 50 million tons of CO2 by 2030. And last but not least is probably the most important one. On the 6th of February, so in a couple of weeks, we will have the publication of the industrial carbon management strategy that will set the legal basis for the deployment of CCUS in Europe. I already had a look at it. It looks quite good. But I will stop here, and I will be happy to take any questions if you have them on it. Thank you very much.
Thanks a lot, Fabio. I think you cannot leave us without giving some more details about the upcoming strategy.
Yes.
You said that you had already a look at it, and maybe you can share a little bit more about it, your expectation for the future adoption, and, I don't know, your vision on it.
Yes, thank you, Antonella. It's some spoilers about the upcoming strategy. So I was also in Aalborg last year at the CCUS Forum. So the strategy is built pretty much on the work done by the working groups of the CCUS Forum that I'm also following. So for me, it was not a big surprise on many aspects, but especially for an external reader, the ambition is very high. To say that, and also to link with what Dominic said, so we have injection capacity 50 million tons by 2030, but in the strategy there is written 450 million tons by 2050. That's what Europe is thinking in terms of what we need to capture. So you can see that, and we are starting from zero, pretty much. So the ambition is extremely high, but that is really the purpose of the strategy, to go through holistically all the value chain. So trying to look at what is needed for the deployment of all the transportation network, the development of the hubs. With the strategy, the Commission will establish a platform to match emitters with users or storage possibilities of CO2, because that's what we need to solve that chicken and egg problem. And then, in particular for waste to energy, the Commission announced in Aalborg then it will create a CCUS observatory to monitor, report, and verify capture CO2 starting from the project in cement and waste to energy plants. So I was happy to see this, and because again, as a sector, we can be also among the pioneers with carbon capture technologies, and as CEWEP, we will help, and we already had talks with the Commission for supporting the Commission in developing this tool and this platform.
Thank you. Thanks a lot. Very interesting, and thanks for sharing with us this spoiler. Very appreciated. I think now we can go to the next speaker, and I'm very happy, to introduce Jürgen REINMANN, which is member of the ESWET Technical Committee and Managing Director at ENVEA. And he's going to speak today about measuring biogenic CO2 emissions from waste-to-energy plants. I hope he will share with us some successful stories and challenges ahead. Jürgen, the floor is yours.
Thank you for that, also for the possibility to speak here. We were talking now a lot about carbon capture and how to reduce CO2 emissions. The other part, what we have behind, is the emission trading system, which is a successful tool, we can say today, also to reduce CO2 emissions and to be a driver to do these investments. If there would be no costs for CO2 emissions, the necessity, let's say the financial necessity to do something would be quite smaller. If we look on emission trading system and emission trading regulations in Europe, we have our emission trading systems since 2005. So next year it will 20 years old, and with that it was the first and it's the oldest emission trading system which exists in the world. So for that here in Europe we started quite early. But the EU ETS applies on power plants, industrial facilities, like for example cement kilns, iron and steel smelting. But there is up to now no implementation of the waste to energy sector. There's an ongoing discussion for that, but it's not yet implemented. Last year was published the Directive 2023-959 in May. And there the Commission defined that it will assess and report by the 31st of July 2026, so in 2.5 years, on the possibility of including the municipal waste incineration sector in the ETS, with a view to include it from 2028. So, as I said before, it's not yet implemented, but since longer time it's in discussion. So what to do, how to determine and how to monitor CO2 emissions. So for that exists the monitoring and reporting rules, which are also called MRR. And this provides that operators shall apply either a calculation-based methodology or a measurement-based methodology to monitor the emissions of their plant. That's described in Article 21. And the European Commission published on October last year the revised monitoring and reporting rules for the CO2 emissions, and here including waste-to-energy plants. The revised monitoring reporting rule was getting into force now on the 1st January 2024. And the reason behind that is what was in the slide before, that in July 2026 it should be decided if the waste-to-energy sector will be implemented in the European Union emission trading system. So, and for that, sure, we have to collect data before to have a base on which this decision in 2026 can be done. So this means, on the other side, that the monitoring of the CO2 emission has to start this year, or started this year in January, to collect data. Even if the waste-to-energy sector has to pay for the CO2 emissions, but they have to monitor, to collect the data to make later the decisions. So what is the motivation then and the difficulty in the waste-to-energy sector to determine the total CO2 emissions? The problem is that municipal solid waste and refuse-derived fuel processed from municipal solid waste and hazardous waste incinerators is a really unknown mixture of fuel. I always say it's very easy to say in a coal-fired power plant how much CO2 emissions we have. We can calculate. It's the same if there are natural gas turbines. It's quite easy, but here by this mixture of undefined fuel, it's quite more complex to determine the total CO2 emissions, but also the biogenic part, which was also mentioned before, is, let's say, greenhouse gas neutral, or defined as greenhouse gas neutral, and for that it's not necessary to buy or to apply for emission trading certificates. If you look for the emission trading regulations in Europe, as mentioned before, the biogenic part is seen as greenhouse gas neutral. The reason for that is if we burn biomass, then the CO2 which is released is the CO2 which the plant, the tree, or what else was absorbing in the last couple of years before. So it's not like the greenhouse gas effect is starting with the industrialization. I always say in the Stone Age we had already CO2 emissions, but at this time it was all biogenic. And the greenhouse gas effect and the climate change really started with the industrialization, when more and more oil, natural gas and fossil materials like coal was burned. And so that's behind this idea that the biogenic fraction of the CO2 emissions is greenhouse gas neutral. Beside our European regulation, we have in the meantime also different domestic regulations, whereby, for example, in Germany, we have our Fuel Trading Act. It's in German Brennstoffemissionshandelsgesetz. We have this in force since a couple of years, and it covers up to now the burning of fuel, like gasoline, like also coal, and all these fossil fuels. We also have to pay by private for that. So due to that, for example, our gasoline was getting more expensive, or the natural gas for heating the houses. So it's something which is already implemented. But from 1st January this year, also the waste to energy sector was integrated in this National Fuel Trading Act. So by us in Germany, we have already a domestic regulation which implements the waste to energy sector. And here, for the correct calculation of the countable CO2 emissions, it's important to determine the biogenic and fossil fraction again, because also in our domestic regulation, certificates are needed only for the emission of fossil CO2 emissions. For the determination of the biogenic fraction, I mentioned mainly the following possibilities. One is the analysis and sampling based on EN ISO 13833. So that's, I will explain later, that's the extraction of the flue gas, sampling on an adsorber, and later of analysis of it. There could be any other method based on a relevant standard, including ISO 18466. This is the so-called balance method. So there are measured different input parameters, heat generation, and so on. And with that are calculated then the total CO2 emissions and also the biogenic fraction of this. Or a method approved on the basis of volume-weighted biomass fractions of the individual waste groups in accordance with related tables, which list specific emission factors for the different waste groups. That's honestly, it's my personally opinion, a quite uncertain method. So in our German Fuel Trading Act, there's a table at the end, and we have the different waste keys, and for each waste key is published a total CO2 emission factor and a biogenic fraction factor. So, but for me, it's when the trucks are coming with a different kind of waste, how good, how accurate we are able to determine how many waste of the different waste keys are in the trucks and are burned later. So, but in the different domestic regulations, always these more or less three methods are accepted. So it's also a method which is aptly applied by the different operators. If we look on these ISO 13833, this is a standard which was already published more than 10 years ago. And it's a determination of the ratio of biomass, so biogenic and fossil-derived carbon dioxide, so and followed by the radiocarbon sampling and determination method. So what we do here, we have a continuous sampling of a part of the flue gas, and we adsorb the CO2 on an adsorber material. After the sampling period, this cartridge is taken out, the next cartridge is installed, and the cartridge is sent to a laboratory to be analyzed with the carbon-14 method. With the carbon-14 method, it's possible to separate between fossil and biogenic CO2, because fossil material consists only of carbon-12 and only biogenic material consists of carbon-14. So in this way, it's possible to determine the fraction of the sampled CO2 for fossil and biogenic. Additionally to that, surely is needed the measurement of the total CO2 emissions on the stack and the volume flow on the stack to have the information on the total mass flow of this incineration line over the years. And Fabio was telling that today is considered that 60% of the CO2 emissions of a waste-to-energy plant is from biogenic content. And I will show results which confirm this partly, but also shows quite different fluctuations. And several countries up to now work with such fixed values. They say, okay, 58%, 60%, 50%, depending on the country, of the CO2 emission of a waste-to-energy plant is biogenic. But this could, at the end, also quite expensive for operators. So how is the functional principle of the system we provide on the market? It's a volume proportional extraction of a part of the flue gas via a heated sampling probe and a sampling line. We have the absorption of the CO2 on an absorption trap filled with ascaride, that's mentioned in the 13833 or soda lime. I have to say we have get better results and better experiments with soda lime, so normally we use this today. Sampling periods could be from several hours up to 1 month, so there we come to the continuous sampling, and this means if you sample 1 month and you analyze these cartridges, at the end you will have 12 analytical results. So means you have to pay for 12 analyses. So these are, let's say, a part of the operating costs, but it's quite helpful. And the sampling principle fulfills all the requirements which are mentioned in these ISO 13833. Here you can see on the left picture on a horizontal duct the installation of the heated probe, and then followed by the heated line, and on the right side you see the cabinet, so it's a possible wall-mounted cabinet with an integrated touch panel for operation. So it's quite easy to handle with that. We have integrated there all our experiences. The ones who knows our company, we are active in the meantime around 25 years in continuous dioxin sampling, and since around 14, 15 years in continuous mercury sampling. So we know quite well what we have to consider if we want to have such an automatic long-term sampling. So I show here results from the project in France, which was also supported by the French environmental agency ADEME, also FNAT, Cabinet Berlin, and we provided the sampler. By this project, and it's also available for download, so it's free. There was done the determination of the biogenic CO2 content and green energy over 1 year in 10 municipal waste incinerators here in France and 1 refuse-derived fuel plant. The amount of the waste burned in these plants corresponds to around 10% of the total amount of waste which is burned here in France per year. For MassBio, they had so Cabinet Malais has a software called MassBio. It's patented method for calculating the biogenic and fossil mass fraction of the fuel and for calculating the green energy. And during this program, there were taken 148 samples from these 10 waste-to-energy plants and 10 samples from the RDF plants. So you can see there is quite a lot of statistics behind already. And so this could give quite good statistical data. So, and when we look on the calculations, at first we found at this time 58% of biogenic CO2 in the flue gas and 42% fossil. So this corresponds to the more or less 60% Fabio mentioned. With that back calculated, was determined that 67% of the waste which was burned was from biogenic, non-combustible. 19% was fossil waste and 14% was non-combustible. So that could be back calculated with this MassBio software from Cabinet Malais, and with that could be calculated a portion of 55% green energy. If we look on that, there are also the requests in the European Union to increase the quantity of green energy. So for that it's also important to know how much green energy is generated by waste-to-energy application. Another interesting results we have from a municipal waste incinerator in a Mediterranean tourist place. These are results of a multi-year monitoring. If you look on the scale, so we started in 2017, so it's also something which is already done for several years. So the application of this method, it's not relatively new. And this incinerator has 2 lines, and partly is also incinerated sewage sludge. And there's no permanent operation of both lines. The reason for that is that, okay, as I mentioned, it's in a tourist place, that during summertime, sure, there are quite more people, so there's needed a higher incineration capacity in comparison to wintertime when there are less people around there. If we look on the biogenic content, the averages were 65.9% in line 1 and 66.5 line 2, so it fits quite well. We should expect that. But it can be seen a trend of higher biogenic fraction in winter and lower in summertime. So each time when the place is full there, the fossil content is higher. And we expect that during the high seasons, when there are a lot of tourists, the waste separation and waste collecting is quite different from winter time. So this means that in summertime more plastics will be implemented in the waste, and because of that the biogenic content is lower. So it's quite interesting, if you look, it varies really between 56 up to more than 70% biogenic. So there are really high fluctuations, and once again, to calculate that could be quite complex. Come to the conclusion. The started action in the European Union to determine the CO2 emissions in the waste-to-energy plants from 2024 lead to the request of a simple and accurate measurement method for the determination of the total and biogenic CO2 emissions. The application of this ISO 13833 is surely one method which is quite easy to handle and which could give quite good results, and it's an interesting tool. The implementation of the emission trading system on waste-to-energy plants in several countries will help to collect information and experiences for this assessment on the European Commission in 2026 for a possible extension on the ETS to waste-to-energy plants. And I thanks for your attention, and once again also thanks for the possibility to talk here.
Thank you very much. Despite the fact that the presentation was extremely interesting, I think I may keep my curiosity for myself because we are running a little bit late, and I will give the floor to the next speaker, and maybe we can save some minutes for questions after the last presentation, if it's okay.
Yeah.
So it's my pleasure to introduce the last speaker, but only who is Olivier BOBIN, the CEO at CIRAM Lab. Is going to present us on carbon clarity, analyzing the biogenic content and origins in the pursuit of EU renewable energy goals. Thank you.
Thank you, Antonella. Good morning, everybody. So I will talk about the radiocarbon analysis, the well-known C14 dating method, in fact, and the use of this technique and the stable isotope analysis too, to test the biogenic part of waste. A short presentation of CIRAM. CIRAM is a French private laboratory. We are a small team of 13 people with a PhD engineer technician. From the beginning of CIRAM in 2005, we have an international spirit. A proof of that is more than 50% of our turnover is made to export. We have three main activities: the analysis of industrial material, the dating of archaeological artifacts, and the scientific analysis of work of art in order to make a scientific authentication of work of art. And finally, as we are a small team, we have very short turnaround for the analysis, between 5 and 10 working days. What we can analyze with C14 test and a stable isotope, we can of course analyze the solids recovered fuels, the waste of course, but also solvents, the oil of second generation. But we also analyze the CO2 emission, smoke from factory or smoke emission. And what we will do, in fact, we will quantify and we will qualify the biogenic part and the fossil part of this SRF and CO2 emission. There is two different ways to define the sustainability. On the first hand, you have the mass balance. I am sure that you know that. Mass balance use a lot of criteria. as professional training, respect of the law, the kind of storage, something like that. Very important thing, yes, of course. But I didn't really understand the link between these criteria and sustainability. On the other hand, you have the radiocarbon test, the C14 analysis. It is a physics measurement. So we analyze the product. We don't analyze the process. It is an objective result without interpretation, without calculation. So for me, mass balance is more an approach when the C14 is a physical measurement. But how does it work, this C14? In fact, C14 is present in all the atmosphere, in the CO2. C14 is a radioactive isotope of carbon. So C14 is present in all living organisms. It's present by respiration and photosynthesis. Radioactive isotope means that C14 is unstable. That means that with time it will transform. So on the first hand, C14 decrease, but on the other hand, during life, C14 is reintegrated inside the organism by respiration and photosynthesis. So during life, there is a balance of C14. From the death of the organism, there is no exchange with atmosphere anymore. So C14 will decrease, decrease, and decrease. And after 60,000 years, it will completely disappear. So the living being, the biomass, okay, contain a full radiocarbon tank. So we will talk about the PMC, the percentage of modern carbon. That means that actual biomass contain 100% of modern carbon. At the opposite, petroleum comes from the degradation of organic compounds over a million years. So the petroleum doesn't contain C14 anymore. So the fossil compound doesn't contain C14 anymore. So if we quantify the percentage of modern carbon, we will quantify the percentage of bio-based carbon. So you understood that the C14 test, you can make the quantification of the bio-based carbon content, but it works on every kind of material. It works on solid, it works on liquid and gas. It is blind test. We don't need to know the composition of the material. We only know if it contains carbon or not, of course. It is a routine technique, though we can analyze a lot of samples a week at CIRAM between 100 and 150. The detection limit is very good, and we have a high precision, under 1%. Of course, we use international standard, which describe how to make this radiocarbon test. There is American standard and European also. An important thing, when we analyze 30 samples, in the same time we analyzed 8 international material to obtain the best quality analysis. So there is 2 solutions to use C14 test in waste to energy. You can analyze the SRF, So you can define the percentage of biogenic parts into your fuel. But you can also analyze the CO2 emission, and you will quantify the biogenic part content of the fuel and the combustive. So you see that C14, you can use C14 test at every step of your process. And you can follow the carbon from the fuel to the emission. A very important thing, it is the homogeneity and the representativity of the sample. Why? Because for the radiocarbon test, for the C14 analysis, we will analyze a very small quantity of material. It represents tens milligrams. So you will understand that if analyze the paper, the wood or the plastic in this SRF, the quantification of the biogenic parts will be different. So for the SRF, we have to micronize, we have to homogeneize the compound to have a result which is representative of the material. And it is the same thing for the CO2 emission. As Jürgen explained to you, we can analyze gas, but if I take a sample for an hour, I think the result will be different if I catch the CO2 for 1 month. So it exists a device to collect CO2 during 1 week or 1 month to obtain at the end a representative sample. I will talk about also the stable isotope analysis. It could be very interesting to couple the C14 test and the stable isotope analysis. Here you see on this graph that we can make the difference of the origin of the fuel, coupling radiocarbon and stable isotope of carbon. You can make the difference between vegetable oil, microalgae fuel, wood pyrolysis. To conclude, I hope that you understood that the C14 test is reliable, accurate, and fast analysis to quantify the biogenic parts of solids, of liquids, and gas. And this C14 test is relevant at every stage, in fact, of your process. The result that we give you is very easy to understand, even if you are not a scientist. But you saw that there was some subtlety about the homogeneity and the representativity of sample. I thank you for your attention. If you have more questions, you can contact us or visit on booth on G17. Thank you.
Thank you very much. Thank you, Olivier. First we want to check, I want to thank all my speakers for the insightful presentations that they shared with us. Thanks a lot. And I want to check if there are any questions from the audience. Okay, it seems that you gave quite exhaustive presentations, but still I have a question, so maybe I can address this question to you, Jürgen, and to you, Olivier, because I didn't do that before. And I want to ask you, what do you think are the main obstacles for waste to energy when dealing with CO2 accounting? Maybe you can start.
Okay, I think the main difficulty is as I said, the inhomogeneous fuel, which waste it is. And so for that, we have to look for and we have to collect experiences, what will be the best and most accurate method to determine the total CO2 emissions and from that the biogenic fraction of it. And one question which is behind there always, if there will be, let's say, a European Union-wide regulation that waste-to-energy sector should be implemented in the emission trading system, and a lot of operators would use such samplers if there will be enough laboratory capacity available. And we are quite convinced there will be. When we started many years ago, it's a coincidence that this Better Analytic is directly here, the booth. They were the only one who were able to do such eco-traded analysis. But today we are more and more, as we also could hear now, laboratories available. So the laboratory capacity will increase when the market will increase.
Thank you very much. You want to add anything, Olivier? Okay, thanks. Yes.
If there are no questions from the public, I take this great opportunity to ask a question. Actually, it's dual. Maybe if you can say what type of C40 analysis you do. Is AMS, scintillation? AMS, okay. And it's also very casual that Better Analytic is just on the other side. But what is better for you as a lab to analyze? Would you rather receive a cartridges with a solid, with a gas bag, or a liquid, for example, in NOH, KOH bottle?
I think the best is the solid which catch gas, because the bag, I don't know how many time you need to fill the bag. It is 1 hour, 2 hours. The problem is the representativity, in fact, because the analyzed is precise, but is it representative of the emission? Is it relevant to clearly, to precisely define the emission? So for me, especially for the emission, the best way is the device of Jürgen. CIRAM and ENVEA are independent. But because this kind of sampling is really representative.
Maybe if I can continue in the sense that not super, and but I can tell you, yes, of course, if you do a batch analysis, of course, is not representative, but also with the gas bag, you can have a continuous system. So you have a device that continuously suck some CO2 and collects it in a bag. And then when the bag is full, saturated, after could be weeks, a month, then you take it away and then you send it to the lab. So there are operators that are also experiencing continuous opportunity with gas bag. You can do it with cartridges, with gas bag, or also with bottles. But the other thing for me interesting, it's if both of you can shed some lights in terms of uncertainties, both of maybe the sampling system and also of the analysis, because Jürgen mentioned that the MRR of the ETS, and it requires some very strict uncertainties levels that actually were set at the same level of regular combustion units. But as we clearly emerged today, waste is very heterogeneous, so it's also more difficult to sample and analyze. And so actually the uncertainty levels are bigger. What are maybe the values in your experience?
The uncertainty of IMS is very good, is around 0.5%, but you're right, the problem is the homogeneity of the material. And how can we do? We analyze 20 to 30 milligram, milligram. So I think the best way is to not to analyze just one sample, but analyze 3, 4, or 5 samples to be to obtain an average composition. But of course, the cost of the analyzed will increase. So you know, that is why it's very important to discuss, that the lab discuss with the customer to define the best solution and the best analytical process. Because for some kind of material, one analysis is enough. But for SRF, sometimes 3, 4, 5 or more will be required.
I'm sorry, if I may, I think we are running out of time, and I'm sorry to interrupt you, but I know that there is another conference scheduled just now, so we really need to close this discussion. And I think we, I don't know if you have anything urgent to say, Dominic?
I've already got the number, 430 euros.
Oh.
Per test.
Yes.
But that's insignificant. I mean, compared to the value of whatever, how many thousand tons of emissions.
Yeah.
So,
We say.
good business.
Thank you.
Well, I think this is a great way to close this discussion, and I think we got extremely useful information that touched upon different sectors from an industrial perspective, but also from a legislative perspective. And I think we really got the feeling of where we need to accelerate and what we need to do to really drive this transition. So thanks a lot to all of you. Thank you for joining us today.